So Anna Soto is a professor in the Department of Immunology at Tufts University School of Medicine in Boston. And she's also a correspondent member in, I don't know the pronunciation, but in Ecole, Normale, Supérieure. And she was a professor of cancer development at the University of Ulster and at the Blaise Pascal Chair in Biology 2013 to 15 at the Ecole Normale Supérieure of Paris. We are extremely happy to have you, ma'am. And is there anything you'd like to tell everyone before we get into the questions?
Simply that I'm very glad to be here. I appreciate what you are doing. And so it's good, always good to meet with young people. They are our future, obviously.
Absolutely. All right. So what is your background? What subjects did you take up in your schooling, graduation, and further studies?
Okay, well, I mean, I studied in a very different system. I was born in Argentina, so my schooling is different than the classical Anglo-Saxon one, and it's more similar to the French and to the German one. So in that case, you don't have, you know, when you go for your baccalaureate or you go to gymnasium or lycée, what you do is you have to take a very sort of already packaged structure of knowledge, which goes through arts and sciences and history. So you cannot escape that. You take that. Then you can do whatever you wish to concentrate on other issues. But I am glad that I did that because I was exposed to a broad range of interesting stuff. Obviously, it's mostly on the Western tradition. So everything that I learned that is not in the Western tradition, it wasn't scholarly. Like, for example, I like the poet Rabindranath Tagore, and which I don't know if I pronounce well, but he used to go to Argentina when I was a kid because he was a good friend of a lady, a writer in Argentina that was the director of a literary magazine. So he was often in Argentina. So I was attracted to that. Then I read about Buddhism, etc. But that wasn't in school. That was something that I did just because I thought that his poems, even though I read them in Spanish, were absolutely interesting, and I like them even today.
Wow, that's very interesting. So how did you decide studying biology was the right choice?
Well, I mean, I was mostly going to study physics.
Okay.
Because I was good in maths and physics, and I liked all that. But at the time I was interested in this, I realized that if you were not extremely successful in physics, you would end up being a teacher, and you wouldn't have your own laboratory, etc., because there were very few physicists. I mean, there were physicists of prestige in Argentina. And actually, one of them was a friend of my father. And but he moved to study geophysics. That wasn't in his main interest, but because of that, he participated in the 1957 International Geophysics expedition. And then the next year, he got trapped in the North Pole. But I mean, I was a kid, and we exchanged letters when he was in Antarctica. And he started sending me specimens from there. And that interested me to consider biology as a possibility, okay? Although I was fascinated by physics. And then I realized that, well, I like biology too, but one of the reasons why I didn't go directly to biology, but to medicine, was because I hate to have a boss. And I never liked that.
Right.
And so I decided I'm going to be a physician, because if I'm good as a scientist, I will have my laboratory and all that. And but if not, I can at least help people and be independent. Okay, so that was a main issue. And then, of course, I mean, I liked science, and I was lucky enough to have my own lab, and the rest is history. But one consideration was totally extra scientific, and was the fact that I am a person that, you know, I would have never thought of going to the army. That is beyond, you know, the realm of the possible regarding what I was as a kid. I just never took, you know, an answer, a no as an answer is not, or you have, I needed a rational answer to things
Right.
and the possibility of having my room, a room of my own, as they say.
Right. Wow, that's amazing. Okay, so what do you enjoy the most about being a professor at Tufts University? And what do you enjoy the most about being a corresponding member at the center? Again, I don't know how to pronounce it, but at the,
Yes, Centre Cavaillès.
yes, thank you. Ecole, Normale, Supérieure, Paris. So, like, what is the experience like at both the places? How does it differ?
Well, it's very different because, first of all, in America, teaching in a medical school is not the most important activity. It sounds horrible, but that is the case. However, in my school, we are proud of being good teachers too. I mean, Tufts is not only recognized because it's a good, what it's called a type 1 or type of university that is a research university. That tells you everything about it. The first in the rank is research universities, okay? And so our medical school is in a research university. So, but both our college, I mean, and liberal arts and all that, and the in the university and the medical school, we try to do good teaching. But at the end of the day, uh, the main aim of the operation is science, experimental science. So there, um, what I enjoy the most is my laboratory and teach the graduate students and the postdocs that come to my lab. Although the professional school teaching is not, I mean, I do it with pleasure and all that, but it's not learning just because of curiosity. There is a lot of the learning has to do there with getting the grades to get to a good residence, say.
Right.
So it's a different framework. At the École Normale Supérieure, when I was a Pascal chair, I taught the course on what I was working on. I mean, in biological theory, and it was the most amazing experience because everyone that was there just for the pleasure of knowledge. And so there were graduate students, there were postdocs, and there were professors as well that came to some of the lectures. And I enjoyed that immensely because everyone was there in the place putting the best uh, of their minds into this operation. And I still love what I do there. That is another type of research. That is my theoretical biology operation, and I'm in France now because of that.
Wow, that's great. Okay. So, can long-term use of, so this is a very technical question. So, can long-term use of hormonal birth control in females increase the chance of cancer?
Well, there are studies that indicate yes, and studies that indicate uh, that we do not know. And the problem is it's a difficult problem because the contraceptive oral contraceptive formulations come in different types.
Right.
So you cannot put all them together. So I think that there is at this point a feeling that it's not a bad idea to do it at a given time, but at a given other time, if you know that you're not going to have more children, you can have a ligation that is not hormonal, or after having kids, you can have an IUD. Even today, there are many women in Europe that opt even if they are nulliparous, they have no children for an IUD, so that because they are much better than they used to be 20 years ago, even 30 years ago. Right now, they are, you know, if you are not convinced that because of the data, you don't know whether or not you will have more incidence of cancer, I think that IUDs work very well.
All right. Okay, makes sense. So why hasn't there been more research into the birth control for men other than just the physical barrier methods?
No, they are hormonal. Well, there are two things. I mean, societal, there is, let's break the issue.
Yeah.
When it first happened, very few women were in science, and actually it happened in my state, in Massachusetts, in Ulster Foundation, when it was developed. And some people hated the researchers that did that, because at that time, that was, 70 years ago, people thought that it was horrible. I mean, that is very hypocritical, because we know that abortion exists and barrier methods exist since ever. And but people like to be, how can I go to separate sex from procreation? I mean, so this is, I mean, some people may have these thoughts in an honest way. I think that is a lot of hypocrisy on that. But anyway, so it was, I think that they tried to do it in women because it was much easier to do it, because we knew what trigger ovulation, and so that happens only once a month. Without, you know, men sperm production goes in waves, means that it's asynchronous inside the testes, but it's going in continua, right? So it's much more difficult as a target for a first time. So there was scientific reason of feasibility to try it first in women. Second, because it was believed that women would like to have control themselves. I mean, how do you trust someone that says, yeah, I am not fertile? What about if the guy is fertile? Okay. So I thought that there are many reasons. I mean, this is not a book study. This is my opinion. The first thing is clear. I mean, the scientific, because it was easier to target, and because you could block ovulation by giving a mixture of estrogens and progesterone. Okay, fine. Then I think that men start to be more interested in also having control themselves, and some men undergo vasectomies. At that point, people started thinking that maybe there was a good way to do hormonal control and other controls, and there are many studies going on. I don't know at what, it seems to be very difficult, because they were trying this, and they have been using doses of testosterone that will block the production of LH. Apparently, doesn't work that well. I don't know, because also you cannot, well, I mean, it's very complex. I don't want to give a seminar here. But right now, there is interest in doing hormonal and let's call it chemical instead of a physical method like a vasectomy.
Right. All right, that makes a lot of sense. So, can you throw some light on your work regarding endocrine regulation of cell proliferation?
Yes, sure. I mean, that is where I started.
Right.
Together with my scientific partner, Dr. Sonnenschein, we thought, like everyone else, that the estrogens induce cell proliferation, and that cells in the organism are quiescent unless they are being stimulated, okay? And so in order to understand that, Dr. Sonnenschein developed the first cell lines. Actually, I went to work with him to the States because he developed the first cell line that was estrogen sensitive, that contained estrogen receptors, so you could work in culture. And when I started working there, I realized that estrogens didn't do anything, that the cells proliferate on their own. And but when you injected them back into animals, they only proliferated in the presence of estrogen. So that was a paradox, and we decided to study that paradox. And what we found was that if you add serum to the medium, but serum that you remove the estrogens from, uh, then serum in a dose-dependent fashion inhibited the proliferation of cells that were targeted for estrogen. And then once you inhibit it, now you can put estrogens and you will block an inhibition. So we started, and there is where my interest in theory starts, because nobody pay attention to the fact that bacteria proliferate as a default state. I mean, it's a constitutive thing in bacteria. We know that is taken as an axiom in microbiology. You know that they don't need to be told to proliferate. And if you remove nutrients, either they die or they sporulate, but they didn't invent the type of quiescence like the one that exists in the cells of our organism. So it seems that with the advent of multicellularity, negative controls were created, but our cells, the same as bacterial cells, given the chance, they will proliferate unless you somehow intervene and don't allow that to happen. So the default is proliferation. That was, in a nutshell, what we did for several years. And that brought me to the feeling, and not only feeling, the realization that I told you that I love physics and all that. Physics is full of theories.
Right.
And that in biology, we have the theory of evolution, which is good because there you can think within a theoretical frame. Science needs theories. Science without theory is kind of a dubious situation. So what happened is that we don't have a theory of organisms, and so that is my Pascal chair work, was to attempt to isolate principles to build a theory of organisms. And we did 3, and we are working on that now, trying to apply that to studying problems of development. So our theory of organisms is a theory for the life cycle since fertilization to death. And so that is the work I'm doing, because I don't think that you can do science without a proper theoretical frame. And in biology, that doesn't happen. If you are interested, I can talk more about that. But otherwise, this is in a nutshell.
Yes, this is perfect for now. Thank you so much. So my next question to you is, how do you think STEM will progress in the coming years?
Well, I think that is also subject to the idea that proficiency in the so-called hard sciences is not just operational. In other words, I mean that you can write some equations, is not the whole thing, because they can become automatized, okay? In other words, we use symbolic language and formalization in order to capture only one part of the theoretical content of physics, and that is very well known. And probably the first one that talked about that was Poincaré at the end of the 19th century, when there was this movement in mathematics. I mean, this is the great era of logics in mathematics. Right. And the whole idea was to try to pass every law, every possible concept into formalization. And he said, don't kid yourself. There is a content that in physics that is not totally reduced to formalisms. And that one of them, I mean, now it's not him, it's myself, is the principle of inertia. You can write the equation. And so among the 3 laws of Newton, you can derive one from the other formally, but not theoretically. The number 1 is inertia, because that one defines exactly what is that, if you are studying forces, what is your belief, okay? So your belief, that is a theoretical concept, is the principle of inertia, that things will keep moving in a straight line at the speed they were, or so, etc. So constant speed. Now, when it deviates from that, that is what you can ask.
Right.
Okay, so it separates what is taken for granted, and when it's not taken for granted, that is your opportunity to understand the system. And that made progress in physics, in mechanics at that point. Okay, so I think that we have to be a little bit less concerned, because I think that the effort is more operational in some cases, because you want the kids to understand that. But I think that, well, to understand it by playing with that. But I think that you also have to find ways to stress the theoretical context of our sciences, so that people would be more interested in the whole content. And I remember that one thing that was interesting in my education is, like, when we started learning theorems, I had an excellent math professor. It was a woman. She was a woman. And she said, well, there are many ways to solve a theorem. So you can learn it, but why don't you try to do it yourself? And so few of us did. And I was one of those. And so sometimes something interesting was like, oh, I haven't thought of this one, she would say. And that was simple theorems. I mean, we are talking about Euclidean geometry, but the pleasure to think and be free, again, is something that is, to me, is incredibly wonderful. And so I think that is part of my upbringing of trying to do science, is this early conceptualization. I mean, being allowed to conceptualize, and being more than not only allowed, but in a way gently pushed, because it wasn't, obviously, you don't expect everyone to have the same interest, but open that door.
Yes, that's amazing. Okay, so what experience book Society of Cells?
Excuse me? I didn't hear you. There was a vacuum.
Yeah, my bad. So what was your experience when you wrote your book Society of Cells?
Oh, well, that was a very interesting adventure. Dr. Sonnenschein and I wanted to do that, and started because of the default state of proliferation instead of quiescence. And we decided that the format had to be a book, because you cannot put all in an article, okay? And so we decided to do a very exhaustive historic search about how people thought about what. And to our surprise, there was very little theoretical content in many cases. We got to some people that were, in a way, saying that the whole potentiality is in the embryo, and the embryo is proliferating very fast. So it was some sort of cells proliferate, but it was never, it seems that people never stop and thought about it. And then we started figuring out why was the case, and this is a long story. So we started also looking at what you could do experimentally at the time people said what. So that took a long time, but it was an incredible adventure. So we sort of summarized it in different chapters. And then we explain also how you have to measure cell proliferation, etc., why the default state is proliferation in bacteria, etc. And so we went to enunciate this first principle of the default state. And then, but when we started doing our work, we thought, because that is what you are taught and is in the air all the time, that cancer is a problem of cell proliferation. And so we started reading as well about cancer, and we saw many puzzles there. Like, one of them is a 1975 paper whereby a lady in the Western, well, anyway, the Western, no, it wasn't the Western, it was in the Fox, what was it?
Okay.
Did an experiment whereby she injected teratocarcinoma cells into an embryo, and the teratocarcinoma were from a black mouse, and that is a cancer from the stem cells of the inner cell mass into the blastocyst, and she found normalization of these cells. So now the animals that were born were like zebra mice with patches of skin that were black and the rest white. And then the second generation could be totally black. That is that she made something that once became as a cancer cell to behave as a gamete, to behave as 50% of the genome of the F1. And that impressed us a lot. But then we started thinking about this very carefully. And we realized that it was a literature that it was never mentioned about all these type of experiments that never fit. And so we proposed a new theory of cancer, whereby the primary problem is not cell proliferation, but is that cancer is a problem of development gone awry. That is that the same way that in order to make an organ, you need stroma, like mesenchyme and epithelium talking to each other in a three-dimensional dance, because things move and one thing touches something else, and etc. That you need these reciprocal interactions in order to get normalcy, to get organogenesis and histogenesis. So we thought, in order to get cancer, you need these processes to go wrong. And then by extension, during adult life, tissues are repairing. I mean, like the mammary gland is undergoing different processes during the menstrual cycle, etc. So in this remodeling, also, there is something similar to the de novo development. So we said that cancer is a tissue-based problem, whereby what is wrong is these interactions, and therefore there is no cancer cells. There are cancers that contain cells. So therefore the cells that are inside are not cancer cells, are cells that are playing a game, the same way that your liver cells are, liver cells there, but you see they can be put somewhere else, they can do something else. So that this phenotypic determination may be reversible, as demonstrated by these experiments of Mings that I come to describe 2 minutes ago. So there is also plenty of, since then, not only our experiments, but experiments by other people. There are about 50 that shows you how if you take cells from a cancer, a carcinoma, and you inject them into normal tissue, they normalize and help the other, do the same as the others. So if you put a cell that belonged to a hepatic cancer in the liver, now it makes the enzymes that will make albumin, or, it will make the same as the liver. And you can distinguish them because you mark them with a marker.
Right.
Okay, yeah. So I think that writing the book, it taught us two things. One, we learned more about what we were doing, and so we could enunciate the principle and the whole process about how you do this type of thing. And so we started to tell biologists to be explicit about what is their worldview, because if they don't have a theory, at least they have to have a worldview that has to be made explicit, that they never do or seldom. And the other thing is that in the middle of this experiment, we changed ideas. And so we started elaborating a new theory of cancer. And it was a wonderful thing. So again, the bad thing about modern times science, biology, is this urge to do instead of to think. You should think and do, but thinking is as important or more important than doing. You need both.
Right. Makes sense. That makes a lot of sense. Okay, so the next question is rather a non-scientific question. So what do you have to say about finding beauty in medicine? What are some of your own favorite works, and what is one quality you think is necessary for an individual to have to pursue a biology field?
well, there are too many questions. Let me read them aloud myself so
Sure.
I don't get lost.
So the first
So
is
you're,
finding the beauty in medicine. So you can answer it, one by one.
which question is that? What number?
The 14th one.
Beauty in medicine. What are some of our, okay. Beauty in medicine and beauty in science. I think that in science there is plenty of beauty. So part of the pleasure of working in the lab is looking at the microscope, for example, or looking at beautiful animals and looking at the beautiful things they do. So that is beauty in science, and beauty about the equations, and beauty about shapes, and beauty about seeing in real time how cells organize into a duct. All this is absolutely beautiful. And um, I think that is one of the pleasures is that, plus I have, my sister is an artist, and I am very appreciative of fine arts, for example, but also literature, etc. And so in medicine, I think that it's the beauty of that is more or less is the contact with people, because the beauty of science is there, but you have to work in a different time frame, because you have to be here and now. And I think that the beauty there is in the relationships you can have with your patients, and how as persons they are important to you, and what you learn from them, because you learn from everyone. So I think that that is the beauty, is the that everyone knows that life is short, and how we interact in life is, I think, could be a very beautiful thing. Also, when you deal with babies, and that is not medicine. I mean, I look at a baby, and the baby is trying to make sense of the world. You see that their eyes, go to movement and things, and then
Yes.
you stare at them for a minute, and they smile at you and all that. So you think, well, they are like scientists. They are, they look around and they think, oh, what a marvelous world, until, life gives you the other aspect of life, the struggle, the disease, the whatever.
Right.
But so I think that I see beauty in all these things.
And that's a really nice analogy, taking babies as scientists and how they look at everything and they get fascinated by it. That's amazing. Okay. So this will be my last question to you. So all the people that have come here, they can start asking their questions in the chat box. My last question to you will be, what any final piece of advice you would like to give to us budding boys and girls in STEM?
Well, the first thing is, I don't like the advice that some people give to young people, that is, you have to make a living. I mean, yes, you have to make a living, but if that is first in your list, we are in trouble. I mean, when someone plays well the piano, they doesn't think on how to make ends meet. I mean, that will happen anyway. You will have to do it anyway. So I think that you have to do what you really feel, I would say fire in your belly or whatever. You get it there and you have to do it. So when you find that, then, I cannot say that you are assured an interesting life because you found it. But it's a very nice company, be it in arts, sciences, be it as someone that creates stuff, being as someone that performs. It's also performing is creative. It's different because you are performing someone else's work. In being an artisan, I see artisans as people I like to deal with. So um, because I see their interest on what they do. I mean, there is this piece of wood and you work on it. I think that it's not only science. There are, in any human endeavor, there is this beauty. And if we are sensitive to that beauty, we should do it. And I think that goes for all of us. That, and then be generous enough to share your gift, and be also good at taking what is offered to you, because science and any other, we are social animals. We depend of each other. And so I see the political situation in the States where people cannot talk to each other. And I think that we should never get to this point. I know that you have similar problems in India and everywhere. Our whole planet is going bonkers, as we say in the States. But I think that it's up to us to uh, try to fix the problems. Yes, of course, but try to try to keep these good things. I mean, being generous, take from what is offered. Take what is offered too. You don't need to do by yourself what is being offered to you. You know, you can learn. That is also very good. And you can do, and you can offer. And I think that is a general ethics. I think that we have to be, from the beginning, very, very conscious about a good ethic. Because what is happening in the world, as I told you about neoliberalism, if you read the ethics, I mean, the way they spell it out is making money is great. That's it. Now we don't have God. So morals is very difficult. So morals is what you can do without being caught.
Right.
I think that that is a bad philosophy. And I know a lot of people that are atheist and people that are agnostic, and they have a very strong set of ethical rules. So it's not God or not God. It's not my God versus your God. It's something about being an ethical being that is fundamental and is really the spine of everything else.
Right. All right. That's wonderful. And that also makes a lot of sense. So Thevis has asked, I don't know if I've pronounced it correctly, but he has asked, can we use nanobots to destroy or remove or even recover or treat cancer cells?
Wait, nanobots to destroy or remove, recover, or treat the cancer cells. I mean, I think that is the idea of destroying cancer cells. I think that all these, I don't know what you call nanobots, if it's nanoparticles, or if it's nanorobots. I think that that is kind of science fiction. And that we go, I mean, all these, yeah, we can do things that get to tissues. The problem is that in biology, and that is why I say that we have to be good philosophers, everything that is aimed at recognizing A or B may go berserk, because if you look at the beginning of the development of a mammary gland, I mean, skin appendages, the mammary gland, feathers, nails, hair, teeth, mammary gland. They all start the same way. They are rather different, right, at the end.
Right.
But if you see what is BMP4 is, I mean, you will see the same elements appearing at the very first step where you see that this skin is producing something different.
Right.
So, and we have only about 30,000 genes. So that means that biological specificity is not one thing brings another. And so that is what happens all the time when you try to target something, because it's not an yes, no, type of thing. Yes, you can kill cells. We already do that all the time. And you can try giving them, you know, if the cell can take A or B, but then say if a cell has thyroid hormone receptor in the surface, and you give a particle that will recognize that, you know, all cells of the organism have receptors for that. And okay, so you get the feeling of all these things very difficult, and that is why they talk about what type of molecule is targetable. which is something that you can really develop a pharmacological agent or something like that. So I don't believe that when in biology you have these historical events, that one thing became another through eons of evolution. You can target that easily.
Okay, all right. So, Mansirath has asked, what do you think are the causes of endometriosis? Do you believe in retrograde menstrual flow theory?
Wait a second. About endometriosis.
Yeah.
I don't see where it's at.
It's
Retrograde menstrual. Okay. I have very little idea about what causes endometriosis as everyone else. We think that it's very likely that cells like this retrograde theory is what is going on, but then you would ask why not everyone get that implanted, okay, because it's a frequent occurrence. What to me was the most interesting thing I ever read is that there were people with headaches, etc., and they look at the lesion in the brain, and then when operated, it's an endometrioma. So it can go through the bloodstream. So it's not always, if retrograde reflux was the problem, why would it appear as a metastasis at this normal tissue in the brain? And it was observed a couple of times, and in living people, like I just told you, and it happened also, it has been an accidental discovery in autopsies. So that, I'm giving you that example to say, well, that obviously went through the blood or the lymphatic tissue, because there is no direct contact with the uterus and the brain, right? So I don't know.
Okay, all right, that's fine. So Rajshri has asked, does a dysregulated nervous system, for example, having past traumatic experiences, impact the development of adult diseases?
I don't know. I think that is one of those questions. See, when we talk about what is science, it's about questions that can be answered. Yeah. I mean, if there is life in Andromeda, it would take so many light years to get there that probably you need, I don't know, 100 generations of scientists and something else to put a probe that will go there. So it's not a scientific question at this point. And I think that there are questions about, trauma is very bad and it affects your whole functioning in a way, and therefore running experiments to know how is it affecting every part of your life is probably something that you cannot do very well. Okay. So I cannot answer that one.
All right. So Thavis has again asked, if we take out all the cancer cells.
Excuse me, but we do know that it's not good for you. So of course, I mean, I think that what I'm trying to say is that from a viewpoint of experiments that said, well, if you have that, now you will have to have liver problems or anything like that. Of course, if you are in a traumatic situation like that, for example, you may not be able to go to work because you cannot drive, right? So that is big. That occupies a lot of parts of your life. That also alters your relationship with other people, because you can be perceived as someone very weird because you don't want to drive a car anymore. You see, I'm not denying that there is something there. What I'm saying is that I think it's absolutely difficult to figure out how that is causing an effect somewhere else and how you have the appropriate controls. Okay, move on.
As well. In the sense, for some people it might work in a certain way, and for some other people it might work in a different way. So it could be subjective to people as well. All right. So the next question is, if we take out all the cancer cells, can we make the cells around multiplying themselves and regenerate that part like the liver?
Well, I think that if you take cells that once belonged to a cancer and put them in a target, they will behave normal. Now, I understand that in a couple of cases, people try to move them around and they continue being normal. Other people have done some other experiments and say that it depends on whether you inject a lot of these cells or not, whether they would be totally normal. But I think that for the most part, what we know is that they become normal. Although, in other words, the mutations they had will continue having. But the important thing is that if those mutations created cancer, how come that when you put them in a normal environment, they behave normal? So therefore, that goes against the standard theory that says that mutations in DNA make cells uncontrollable and they will proliferate all the time because you inject them and they have all the mutated oncogenes that you want them to have and they will behave normal. So, you know, I think that the question, what those things show is first that if you know how, you can normalize cancer and that will be a good therapy. And there are people working on that, how to normalize cells that once became a cancer.
Yeah.
And because the idea is that it's the process of carcinogenesis that is affecting a tissue. And therefore, if you put cells that went to that far with a good overdose of normal cells, because story, if you inject them subcutaneously in the millions, they will do a cancer. But if you now put them in a ratio of 1 to 5, 1 to 10, with normal cells in the mammary gland, for example, they form normal ducts. Oh. Would you mind for a second that I answer this call? That will take a second, sorry. Hello?
If anyone else has any questions, you guys can put them in the chat box.
Yes.
Yes.
I was expecting a delivery that was supposed to come in the morning. It didn't come. And right now he's in another address. Thank God that I answered because it was going to be delivered somewhere else. Okay. And it's just the pharmacy anyway. Okay.
Yeah, all right. So, Prakriti
Sorry.
asked, no problem at all. Prakriti has asked, does the trolley problem analogy apply to ethics in science? if experiments cause immediate pain to participants or even long-term harm, but the results would be beneficial to the society as a whole, what do you think? Should we go ahead with it?
I don't understand this question because it's too general. That depends on what you are doing.
Mm-hmm.
I mean, are you trying to, the amount of pain that you can tolerate depends on what is that you are trying to save, right? I mean, in the past, when people had to amputate an arm or a leg without anesthetics, it was done. Okay?
Yes.
So the idea was, do you take gangrene or you do it? And how it was done in those times, I don't know. But probably I would have gone for amputation rather than dying of gangrene.
Yes.
Okay? But it's up to the patient. But I think that this is something that it has to be in a specific case. I think that the way it's enunciated there, I would say no, it's not for first of all, I don't think that I would approve of an experiment like this when I'm a member of the ethics committee.
Mm-hmm.
And especially if it's for the society as a whole. I mean, the way it's written here, my answer is no way.
Mm-hmm. Yes.
It's absolutely no way. Okay.
If you want, you can clarify, or you can, be a little more specific with your question. So yeah, okay. But for the time being, we'll move on to the next one. So Rajshri has asked, what is the efficacy of RNA interference mechanism in cancer therapy? What other areas could it profoundly impact?
I think that we are in an area where nothing makes sense there because it's like, again, a world without theory. And we discovered those RNAs and we do not know. It's again, maybe they found my address. Could I mute myself and then I can?
Yeah, sure. If anyone else has any questions, you guys can put them. Prakriti, if you want, you can also unmute yourself and clarify.
Okay, I'll do that once she's back.
Yeah, once she's back, let her answer Rajshri's question about the efficacy of RNA interface, and then you can clarify.
Okay, thanks.
Yeah, no problem. This session will go on for another 5 minutes or so. After she has answered both the questions, then yeah, okay, ma'am is back.
Going to give me the package at the elevator. It's just 1 second. Sorry about that. It should have arrived in the morning.
No problem. No problem. Okay.
Do you have a minute or not? So
Yeah.
the question was about, I think that it's a very long answer for a very, as they say, the jury is still out, but it's the same problem as usual. There is no theory, no good theory, and people are trying. And what is happening, even at the experimental level, is not, as far as I can see it, very promising. But there is a lot of money involved, and that is the other ethical problem. I'll come back in a second.
Sure. Prakriti, that will be your cue. As soon as ma'am comes back, you can ask her.
Okay, I'll do that.
Yeah.
The mask. Okay.
If any of you have any other questions, you can again just put them in the chat box and ma'am can answer those. Yes. So the trolley problem, the person who asked the question about ethics, she would like to, make her question a little more specific. So Prakriti, if you could just ask your question.
Yeah, hi, I'm Prakriti, and I just wanted to know about the ethics in experimentation that leads to more research. I guess when they were discussing digestive enzymes, a person was shot in the stomach, and then someone did experimentations on them, and that's how we now know about the enzymes in the digestive system. But that person at that point of time went through a lot of pain for us to get the information that we know now. So was their pain justified for our information, and how do you deal with ethics of experimentation was my question, but I guess it was a little vaguely worded.
Well, I think that first of all, I think that what we know about digestion enzymes is not a person that was shot in the stomach. If I understand well, this was done with animals, okay? And it was done in a time and in a time in which anesthesia wasn't good. And so experimentation in animals was being done in conditions in which the animal had pain. But in here, what they did is an operation where there was a little, you had a way to get into the stomach with a catheter. I understand. I am not this completely sure, but it wasn't in humans. I remember that when I studied this, the cephalic phase and stuff like that, that was those were things that were done in animals. You shouldn't make humans suffer just because you are going to learn something. That is clearly something that is not approved in the States in our committees that approve experimentation in humans.
Right.
This type of thing, I mean, many years ago, it was done in prisoners and things of that sort. And then there is the Helsinki Convention that totally prohibits all this type of thing.
Right. All right.
So
Okay.
that is,
Okay, thank you so much for answering my question.
you're welcome.
Okay.
And
So
sorry for having the delivery 2 hours late, but
all right. It's all right. So Rafaela has asked, who was your scientist inspiration for pursuing the course of biology?
I think that my first inspiration for science was Marie Curie, the physicist, because she was a woman and she could get a Nobel Prize in 1907 or something like that. I mean, it was a long time ago, and I was a kid and I was 9 years old. And I was in a nice pampered situation because, as I said, the friend of my father was a physicist. My father was an engineer, and my mother was a literary person, and so I was exposed to a bunch of things. And not, I'm not talking about being rich. That is a different thing. But being exposed to intellectual stuff, and I remember the specimens that my father's friend sent from Antarctica that opened my mind that it's not only physics that matters, but the idea that Marie Curie could do it sort of was part of my formation as a woman that is now a scientist. And that at the beginning, I was not even conscious that it wasn't open to women, all these things.
Yes.
And that because I was a girl and I said, pampered by these old men that talked to me, and my mother that was a very cultured person and wrote very well and taught me about poetry, literature, and all that. So I didn't see a difference in what my mother was and my father and all these people and others. I mean, I'm not going to enumerate them. My aunt was a very good cello player. The other one taught violin. So, well, okay. I had all these things. I didn't have any idea that women, it was very difficult for women to become anything. And, you know, so I wasn't yet knowing that I would have to have a very special situation because of being a woman. Okay. So, my inspiration was, as I said, in one sense, Marie Curie. I thought it was cool. And then in biology, at the time I was young, there were a couple of people that were very famous of the School of Physiology, and that is why I decided to study, because Argentina is population-wise is small, but in reality is a chunk of I mean, a country compared to the European countries that go from the Antarctica to the tropic. Okay, so I thought that these two guys that were every year candidates to a Nobel Prize, and one got it when I was a kid. So it was already, by the time I thought of all these things, he had already been laureated in 47 or 50. So, and then one of his disciples got the Nobel in 1970 when I was already in medical school. But there was always this tradition of physiology and all that. So these people, just to see them in the TV or you know, it's like some reality close to you.
Yes, yes, absolutely.
It's not like, you know, only Americans or French or whatever would get the Nobel Prize in biology. So in medicine was, sorry. But it was a certain proximity. And when you have this certain proximity, it makes sense. Then when you go to medical school and you see at that point that although we were many students of medicine, 40% of us were women.
Yeah.
Professors were in their great majority, except two women, they were all men. And then you start realizing what's cooking.
Yes. Yes, I understand what you're saying, because until unless you haven't experienced it since a very young age, you don't see it as a problem. But then when you say get into the field and then you observe the community in the field, that's when you realize the disparity.
Yeah, you think that is a problem when you get to the outside world, because in your home, you didn't feel that. So that was privilege in a way,
Right.
because I thought that this sky was the limit.
Yes, absolutely. Okay, so I think this will be our last question, which is immunotherapy a turning point in curing cancer?
Well, that is, as they say, the jury is still out. I think that there have been extraordinary responses in a very meager amount of people. So the optimists think that it's a question of doing more research, and the pessimists think that maybe it's functioning, but not because of what we think is making it function.
Okay.
So I think that we do not know, and like anything else that is infiltrated by money, but I'm talking about humongous amounts of money, it
Right.
gets perverted. So you have the patient, you have the science, and you have the money that goes with it, that, as you know, could make things very nasty.
Yes.
And very and can distort reality.
Yes.
So that is why I'm saying that ethics is number one.
Yes, absolutely.
Yeah.
All right. So
Okay.
thank you so much for doing this, ma'am. It was an absolute pleasure having you on board and giving you all of your invaluable experiences and your insights. It was truly amazing to have you.
Well, thank you very much, and I hope that you will sometime bring someone to tell you how bad is neoliberalism, because you also have to understand. You have to understand up to a certain point how much these things of the world where we live impact what you do.
Right.
And so maybe you would like to distribute that to the group, what I gave you.
Absolutely. I will do that. I will do that.
Okay.